Since harmonic measure is defined in terms of a domain omega, it's natural that the geometry of the domain omega affects the properties that the harmonic measure for that domain has. And in particular, one kind of domain where the geometry of the domain implies very nice properties about the harmonic measure are non-tangentially accessible domains, which were introduced by Jerison and Koch. The definition of an NTA domain is actually comprised of several different definitions, so we're going to go through each one of them in turn. So the first condition is the corkscrew condition. So we say that a domain omega in Euclidean space satisfies the corkscrew condition if there exists some universal constant c, so that for any ball centered on the boundary of our domain, so let's say this is omega here and this is omega complement up here, for any ball centered on the boundary of our domain omega, we can find a ball contained in the complement of omega inside this ball whose radius is at least this constant c times the radius of the original ball. Okay, so you should think of this condition as saying that the along the boundary, the complement of omega is uniformly porous or is uniformly large. The next property that we'll need is the Harnack chain condition. So the Harnack chain condition says the following. So suppose that we're given a pair of points x and x prime in omega. So let's say these are these points right here. And suppose that there exist constants rho and lambda so that the points satisfy the following inequalities. So recall here this notation. Delta of omega x is equal to the distance between x and the boundary. Okay, so suppose x and x prime satisfy for these constants the following inequalities. That the distances between x and x prime to the boundary are at least rho, and furthermore that the distance between x and x prime is less than lambda times rho. So you should think of this as saying that the points x and x prime aren't that much closer to the boundary than they are to each other. And in particular, they are no more than a factor lambda closer to the boundary than they are to each other. Okay, so the Harnack chain condition says that whenever you have a pair of points x and x prime satisfying these inequalities, so they aren't too much closer to the boundary than they are to each other, we can find a chain of balls in omega starting at x and ending at x prime. So the first ball here is B1, the first ball here is Bn. And by a chain, I mean that consecutive balls in the sequence intersect each other. So if this is Bi and this is Bi plus 1, then we always have Bi intersects Bi plus 1. Okay, so there exists such a chain of balls such that furthermore, the length of the chain is no more than a constant depending on lambda. And moreover, that these balls avoid the boundary. Their distance to the boundary is comparable to their sizes. Okay. So why is this an important property for harmonic functions? Well, as the name suggests, recall that Harnack's inequality says that if we have a ball B, then and we have a positive harmonic function in B, okay, then the minimum of u inside this ball, and assume that this ball is also far away from the boundary of omega, that the minimum of u inside this ball is comparable to the maximum of u inside this ball. Okay, so what that means is that if we look at u of x, okay, u of x is going to be comparable to u at any other point inside the ball B1. But because these form a chain, that means that B1 intersects the ball B2. So that means that, let's write this. So u of x is comparable to, let's say, u at the center of B1, okay? So now u of B1 is comparable to u evaluated at the point of the intersection of B1 and B2. And that value is comparable to u evaluated at the center of B2. So this is comparable to u of B2. So this is by successively applying the Harnack's inequality to each one of these balls. And so then we can continue this. And then what we get is that at the end of the day, u of x is comparable to u of x prime with some constant depending on the length of this Harnack chain. And because the length just depends on the number lambda, so really the value the constant in this inequality, in this comparison, just depends on this factor lambda, or in other words, it depends on how much closer the points x and x prime are to the boundary than to each other. We finally arrive at the definition of a non-tangentially accessible domain. So we say that a domain omega is non-tangentially accessible, or NTA for short, if omega satisfies the Harnack chain condition, and both omega and its complement, so the exterior domain, satisfy the corkscrew condition. Okay, so that means, so there are, between any pair of points, we can find a sort of short Harnack chain between those pair of points contained inside the domain. And then for any ball center on the boundary, we can find the large ball contained inside this ball in omega. And we can find a large ball contained in this ball in the complement of omega. Okay, so one can show that familiar domains like C1, like connected C1, one can show that familiar domains like bounded C1 domains or Lipschitz domains will be NTA domains. However, NTA domains don't necessarily have to have differentiable or anywhere differentiable structure. So for example, the interior of the von Koch snowflake will be a non-tangentially accessible domain. Now, the reason why NTA domains are so important is because the geometric properties imposed on them by the definition imply very nice properties for the harmonic measure. So in this theorem, we'll go over some of the properties that harmonic measure satisfies in these domains without giving their proof. So let's suppose that we have a NTA domain omega, and that it satisfies the NTA domain with some constant c. And let's suppose that we have, so let's say this is omega up here, and let's say we have a ball B centered on the boundary, and we have a corkscrew point Z, so a point inside the ball B that stays far away from the boundary of omega. So the first property that we have is that the harmonic measure of this ball B at the corkscrew point Z inside B is at least some constant, universal constant depending on the NTA constants. So to motivate why this should be true, let's consider the probabilistic definition of harmonic measure again. So this isn't how it's actually proved, but this just gives some intuition. So let's say this is our ball B and this is our corkscrew point Z. Now recall that the exterior corkscrew property, so if this is omega, the exterior corkscrew property says that inside this ball, there must be a large corkscrew ball contained in the complement of omega inside this ball. So this says that this implies that the complement of omega inside the ball B, and hence the boundary of omega inside B, is quite large. And so that should mean that if we start a Brownian motion at Z, then it should have large probability of first hitting the boundary of omega inside B than it would anywhere else. The next property concerns a relationship between Green's function and harmonic measure. So we saw earlier in another video that there is this equation relating harmonic measure and Green's function. However, for NTA domains, we actually get some nicer estimates. So the first one says that if we look at Green's function of x and y, and we fix x to be some point outside 2b. So if this is our picture here, x is some point way out here, and this is our ball B. Then if we fix x and then take the supremum of the Green's function as a function of y times rb to the d minus 1, and we take the supremum over this ball, okay, then this is at most the harmonic measure of this ball with pole at x. And in fact, if we, instead of taking the supremum of this function, we instead plug in the corkscrew point, z, for this ball, then we actually get comparability. So this rb to d minus 1 times g of x comma z is actually comparable to the harmonic measure of this ball with pole at x. We also have that harmonic measure is a doubling measure in the following sense. So again, if we have a ball B centered on the boundary and we consider points x far away from this ball, so just contained outside the double of this ball, then the harmonic measure of the double of this ball B is at most a constant times the harmonic measure of B. Finally, we have the following property that if we consider a point z naught outside the double of 2b, and again, we're letting z be a corkscrew point for the ball B, then for any Borel set E inside the ball inside the boundary of omega, we have the following inequality, that the measure of E with respect to the pole Z naught divided by the measure of the ball B containing it with respect to the pole Z naught is comparable to the harmonic measure of E with respect to the corkscrew point Z. Okay, so you can think of this almost as using the Brownian motion interpretation again as sort of a guide. You can almost view this as a conditional probability statement. So this is saying that, you know, if you were to move this over to the other side and write omega z naught of E is comparable to omega z of E times harmonic measure of z naught of E, of the ball B, okay? So recall that the picture looks like, so here's B, here's Z, and here's this point Z naught all the way out here. So sort of what this is saying is that if we have a set E inside the boundary here, it's almost like saying that the probability of a Brownian motion starting at Z naught will first hit the boundary inside the set E is the same thing as computing the probability that first a Brownian motion starting at Z naught first hits somewhere inside the ball B, and then computing the probability that starting inside the ball B at the corkscrew point Z, that the Brownian motion first hits the set E. So this is not at all how it's proved, and it's not exactly accurate, but I see that as kind of a useful mnemonic to remember this rule. So the next lemma concerns not harmonic measure, but harmonic functions in non-tangentially accessible domains. So loosely speaking, the lemma says that if we have a harmonic function u that's non-negative inside the domain omega, but vanishes continuously on the boundary, it actually vanishes even better than continuously. It vanishes wholly continuously. So in particular, let's suppose that we have a point C inside the boundary of omega, and suppose that we have a radius r, and we consider the ball BCR. And suppose that we have a non-negative harmonic function defined in the double of this ball, so that it vanishes continuously along the boundary of omega inside this ball. Okay, so if you have a function satisfying these conditions, and it's also continuous on the intersection of the double with the closure of omega, then there exists some number alpha bigger than 0, so that for any point x inside this ball, the value of u at x will be at most a supremum of u inside this double ball times the distance between x minus c over r to the power alpha. So the special case that we're going to employ this lemma is for when u is the Green's function. So recall that Green's function is a function that vanishes continuously everywhere on the boundary of a domain. So let B be a ball centered on the boundary of omega, and let y fix some point y in omega far away from the ball B, so outside 4 times B, let's say. Then we define the function u of x equal to rb to the d minus 1 times Green's function of x comma y, at least for values x in omega for x not equal to y. And then outside of the domain omega, we just set u of x equals 0. So this function is continuous everywhere in Euclidean space apart from when x equals y, and it's harmonic everywhere in omega except when x is equal to y. So then one can show using the previous lemma and some of the other previous lemmas that for pairs of points x and x prime inside this ball, that the difference between u of x and u of x prime is controlled by the harmonic measure of this ball times x minus x prime over rb to this power alpha. So in other words, the function u of x is a Holder continuous function inside the ball B. And in particular, Green's function will be Holder continuous inside every sufficiently small ball centered along the boundary. So this is going to be important for us later, because later on we're going to take sequences of Green's functions for a sequence of domains. In particular, we're going to blow up our domains around a point on the boundary. and rescale the Green's functions. And we're going to need some way to be able to assert that we can pass to a subsequence so that these Green's functions converge uniformly on compact subsets. So knowing that they are uniformly Holder continuous will allow us to use Arzela-Ascoli later on to conclude this.